Yep, I think started recording here. Good morning, everyone. So today we are going to discuss this problem. Implement a function to check if a linked list is palindrome or not. So here actually there are two approaches. We will discuss these two approaches. How can we do this? I'm already revealing actually the two approaches here, but we can discuss and find out these two approaches. So the idea here is let's look at the example here, right? Initial link list. What is this? Okay, is the palindrome or not? Yeah, this is the one. So if you look at this, 1 2 3 2 1, right? So is linked list palindrome? True. Palindrome is basically um, half of the, like, first half resembles the second half, right? So if you reverse, basically another one is like if you reverse the linked list, it will be the same numbers, 1 2 3 2 1, but at the same time if you start from the last, 1 2 3 2 1, right? So it's the same numbers if you go back and forth. So second one is 1 2 2 2 1. Is it palindrome? That is also palindrome, right? So the main difference between the two is first one is the 5 elements, second one is the even number of elements, which is 4 elements. Correct? You guys following so
Yep,
far?
yep,
So
yep.
So this is a linked list. I think we discussed in the array time. We already discussed different approaches. Palindrome array. If I gave you array, we can easily do whether it is palindrome or not. There are different strategies if we are working with arrays. But how can we do in a linked list? Right, linked list is like first node connected to second node and this way, right? So you cannot um, you cannot go reverse. That's the main problem with the linked list. But how can we solve in the linked list way? Okay, so I already put two approaches here. Can you guys any hints from this approach one? Basically, reverse and compare. Anyone can explain how they do the reverse and compare?
Yeah, maybe like you can do the take the reverse the first element from the reverse and the same element from the first one. Then we'll check that.
Yep.
So the last element, first element is the same or not.
What is that? So reverse, right? So basically, first option here is reverse and compare. So what is meant by that? So you're saying we need to reverse the elements, right? Srini, what is the approach you explained? Can you repeat? We can also use the whiteboarding here actually. So let me get a pen here. Just I forgot to take the writing pen. Just give me a minute. Okay, I'm back. So uh, reverse and compare. So let's take this one, right? Let's take an example. So here are the linked list nodes, right? So let's say we have 1 2 3. Okay, so now what we do is the 3 is like, anyway, this is ending node. The next value will be null. Correct? So we need to know whether this is a palindrome. If 1 2 3 is not a palindrome, let's say if we have 1 2 1, this is a palindrome, right? If in, even if you go from back, it is having the same exact sequence of numbers. Correct? So how can we do this? If we have 1 2 3, right? So we have head always points to the first element. So how do you know whether these are in a palindromic sequence or not? One option, as I mentioned, is reverse and compare. Basically what we are going to do is we can reverse the elements in a new linked list. Just a minute. So the idea here is we'll create another list with the elements in the reverse order. Basically, if we have 3 2 1, then what we can do is we can compare one by one. We can compare these two elements, we can compare these two elements, we can compare these two elements. Whenever we find elements which are not equal, then we can simply exit the loop and say this is not a palindrome. You guys understood the approach? Srini and Modit, are you guys following so far?
Yes.
Yes.
So basically, there are two approaches. First one is reverse and compare. So reverse is we are reversing the entire linked list. We are not modifying anything. Basically, there is a way. So we can take another variable. We can set off another linked list, and we can create the linked list in a reverse way. That is another first algorithm. Is basically there are two steps. First step is reverse the given list and create this reverse linked list, and then second step is compare one by one, compare first element with first element, second element with second element, like that. So this is the one algorithm. Now, before going into the code, let's discuss the pros and cons of this algorithm. So first of all, there are two times, like there are two things we need to consider. First one is time complexity. Second one is space complexity. So coming to the time complexity. So let's say we have linked list with n elements. Here n is 3 here. We have n elements, right? How many times we are navigating with the n elements? First of all, in order to create the reverse linked list, we already need to navigate the entire n elements. So that is n times you already navigated. Plus, when you navigate n times, you created another linked list. Now, in the step number two, we are navigating again n elements, right? Which is 2n. Time complexity is 2n. Two times you are navigating n elements. Is it clear? Time complexity TC.
Mm-hmm.
So now come to the
Yes.
space complexity. What is the space complexity? Can anyone tell the space complexity? Space complexity is basically how
Storage.
many, sorry, go ahead. Yeah. How
Yeah.
much spaces we are using. Yeah.
Correct. Storage.
Yeah. Storage. How much extra storage we are using for this algorithm.
So I think space complexity will be length of linked list only, like
Exactly. N.
n, like big of n. And
O of n. Yeah. So the O of 2n, basically 2n is also considered as n actually. So we usually omit the constant variables, right? Whenever we are saying complexities, we no need to consider the constants. So order of n for time complexity, order of n space complexity. You guys clear, right? Why it is order of n, why it is on both space complexity and time complexity, right?
Yes.
So now coming back to the second approach, how can we optimize this, right? Because like let's say here in this, like let's execute this algorithm. First algorithm in the first example, we got 1 2 3 becomes 3 2 1, and we compare these two elements, and we immediately will say 1 is not equal to 3. Then we'll immediately say this is not a palindrome. In this case, what happens is 1 to 1 becomes again 1 to 1. This element we are creating here, this element here, this element here. So basically we will create a reversal linked list. Now these two are matching, these two are matching, these two are matching. So this algorithm works. This is giving whatever we want, true false. But now let's look at the space complexity is time complexity. We are taking order of n. So is there any way we can increase? I don't think there is no way to optimize the space time complexity, because you have to you have to navigate all the elements, right? Without navigating, you can't even say whether it is palindrome or not. Correct? You have to navigate all the elements, which is order of n. I don't think you can create an algorithm with order of 1. You guys agree with me or not? Right? So we
yes, we need to like iterate the whole linked list through a whole
exactly.
linked
So
list.
yeah. Without navigating, basically without navigating all the elements, we can't even tell whether the elements is a palindrome elements or not. So let's think about optimizing the space complexity, because we cannot, whenever in interviews we always, if you come up with an idea, let's look at the space complexity and time complexity, and then an interviewer will ask you, hey, can we optimize this? If he likes the idea, before he asks you to code, he will ask you, hey, your idea is good, but can you optimize? That optimize means he don't give you optimization in terms of space or time. It's up to you decide. As a candidate, we need to decide, hey, okay, let me think, how can I optimize this? Then you think, what is possibilities, what possibilities are there for the given algorithm. In some algorithms you cannot optimize in the time. This is one of the example. You cannot optimize the time anymore. You have to navigate all elements at least once. So there is no way of thinking about optimizing time. The only way is we can think optimize the space, because it's unnecessarily you are creating another entire linked list. Look at this. If you have million elements, if you have million elements in the linked list, you are creating one more million elements linked list, which is like, which is obvious, which is like not a good good idea to create another set of whole given input, right? So how can we optimize the space? By utilizing the existing linked list itself. So here, in this algorithm, we are always thinking about, hey, just create another linked list and then just compare these one by one. But instead of creating another linked list, okay, which is of order of n, can we use any other data structure that can optimize the space, without even storing all the elements of the given linked list? So any ideas, so to optimize the space? Srini or Modit, any ideas?
No, like no.
Srini, any ideas? So basically,
You're saying instead of a linked list, we can look for some other
yeah,
data structure.
yeah. If you use any other data, we have,
Uh,
we have arrays, we have hash tables, we have queues, we have stacks, we have graphs, we have trees. These are all different. If you use another data
Probably,
structure, that will
uh,
optimize.
probably array could be the
Let's
better, I
talk
think.
about it. Yeah, let's think about it. How the array is helpful. So how are we going to do this? So what you do with array? So you'll take an array.
You're saying, okay, let me understand the problem statement first.
Yeah,
So you're saying that instead of having the first one itself in the linked list, you're thinking of changing that whole the storage. Instead of a linked list, you want to use another mechanism called array, right? Or
exactly.
you're saying instead of the second one, you want to use the some other one.
So first one is the given linked list. The problem
Okay,
statement, we
got it.
cannot
So,
we cannot
mm,
change the input. Input is
okay,
always like a given a linked list, given a linked list. Find
I
out
see.
whether this is a palindrome or not.
I see.
We don't have
So
any control on the input. Input is always a linked list. Okay.
okay.
In the
So
first
then in that
request, we are
case,
using another linked
yeah,
list, which is something is not, it's bothering us, because we no need to use another. We don't want to create another big linked list which is equal to the given input, right?
I see. I
Yeah.
see. So in that case, then instead of like a array,
Mhm.
this hash table will be the best one, so that you can easily check whether it is present or not.
Let's start with hash table or hash set. So
Mhm.
how can we do that? So let's say given input 1 2 3 is there. Here is the hash table. So do you want to use keys and values, or just keys?
Just keys is fine, I
Okay,
think. Yeah.
okay. Let's put the keys. So no values. We'll put the one. We'll put the two. We'll put the three, and then we all three elements are done. How this will be helpful to figure out palindrome?
So we know like a n number of items, right?
Yeah,
Basically.
number of items. Okay.
So based on that, like we make sure that the first item is like every time whenever the item is present or not, we'll add it.
Okay.
So
Yeah.
till we like if you reach middle of like maybe if you know the count of the linked list items.
You coming to the point. Yes. Okay. How do you
So
know? How do you determine the count in the linked list? There is no concept of count. You have to determine ourselves. We have to determine ourselves by navigating all the elements, right? Linked list,
yeah,
the input is only the header.
header, right?
Yeah.
Correct.
Okay.
I'm trying to solve my so it's been right. I see. Correct.
Yeah. So, but go ahead. Go ahead with your algorithm. Let's say if you know the count. Let's say we know three elements. What do you do with the with that input? If you know that three elements are there, and how it will be helpful for the hash table.
So after the second, we expect that the item should be present in the your hash. If it is not present, means that's not a palindrome.
What is that? If you, sorry, I couldn't understand. So let's say in this
Suppose.
example, one, two, three, right?
Mhm.
Okay. We added one in the key, and we added two also. We added three.
So before while the three itself,
Mm-hmm.
you will know like if you know the three items, right?
Mm.
So the third item should have been present in the because you will do the divide by off.
Oh, okay.
So after the third element should definitely present in your hash set. Otherwise, it is not a palindrome. So you'll be determined with the off loop itself instead of
Mm.
like the whole traverse through the entire linked list.
Okay. Okay. So
I'm
basically,
not sure. Does it make sense or not? Because I'm little
but
bad on the.
it's yeah, it's still it looks like there is an idea it is coming up. I think it could be possible. What you're saying is right now the length is three. 3 by 2 is actually the integer two one, which is
Mm,
integer division. 3 by 2 1. You can
mm.
add one plus one, which is two. Basically, divided by two plus one. That will give you the number of elements. So you can add only two elements. What you're saying is whenever you get a you are trying to add more than two, then definitely that is a not palindrome, which is a good idea. Actually, I like it because let's run with this approach. This is also the same thing. Three elements, you added one two there. Now you are trying to put the third one here, which is you can safely say one is there. Now you are completed linked list. You did not add more than two. Very good algorithm. This is actually good algorithm, and so you added only these number of elements. So it's a palindrome. Yeah, it's a good idea. So there is no problem. I don't think it's any problem in this in this algorithm. But there are we can use another data structure effectively as well.
Mm, mm.
The one I studied in the book is different. It did not use hash table, but that's fine. This is also good algorithm. So did you understand, Modit, what Srini suggested here? Modit,
Um,
yeah,
yes. Can you like repeat like
I can repeat. Yeah, I can repeat.
yeah.
So what Srini is saying is basically first step is okay. I think we can erase and do it again. So what if I understand? Correct me if I'm wrong, Srini. So what he's saying is first of all, first step we will count the number of elements. We got three, right? So second step is we'll divide it by number of elements, which is n by 2 plus 1. That is the max number of elements you can put in the hash table or hash set, whatever it is. That means in this case number of elements 3, and 3 by 2 plus 1 is, which is 2, right? So basically, so 3 by basically integer division. When you do the integer division, 3 by 2 plus 1, which is 2, correct? So that means you can put only max number of elements 2. That means only half. If you divide the entire linked list by 2, if you can if you are putting only these two elements. But I think it doesn't. I think it is one way it is failing, Srini. I think I'm guessing. Let's say if you are having a list like this, 1 2 1 2, the 2 1, if you reverse this it becomes 2 1 2 1. Is it palindrome? No, right? See, 1 2 1
But
2 is
but
different
wait,
than 2 1 2 1. If you are, but you are putting only 1 2 here in the hand, but this is not a palindrome. I think it is only occurrence count. The hash table is giving occurrence count rather than sequence. You are not checking the sequence, correct?
true. Yeah, yeah. I realize that. Yeah, maybe if you try with the indexing, it
Yeah.
yeah. If you try with indexing, it will work. But yeah, I see because
See,
of the Yeah, if you are only depend on the key item, if it the repeat like a repetition may fail. I see.
Yeah. So now I found the case which is failing. One to one is working, but if you have something like this, basically, so Modit, what Srini suggested, put the items whichever is occurred here. So see, one to only two times occurred, and one is all two also two times occurred. We are thinking it's a palindrome, but sequence is different. Even though one to, if you reverse it, it becomes two one two one. So this is not equal to one two. If you are reading from the back, it's not equal to if you are reading from the front. So the hash table algorithm may not work in this case unless we
Right.
unless we attach the index as well,
Yes,
which is
yeah,
also difficult. The indexing
correct,
is also difficult because linked list doesn't give you index. You have to track
correct.
on our own. It's not like array, right? So that's why this algorithm is failed in that situation. But let me reveal the actual solution. Are you guys ready?
Go ahead.
So basically, if you use a good data structure, our friend, before giving you that hint, let me tell you what we need to do. So I don't want to reveal the final data structure that we're going to use. So I will give you the idea. You will definitely able to figure out. So the idea here is a big linked list. The idea here is in the arrays we already did that. So the linked list, the palindrome means if you start reading from the back, right? Oh no, yeah. So the let's say if we divide the linked list into the half, okay, if you divide the linked list into the half, this is the first half and this is the second half, right? So these elements, the second half elements resembles this element, right? Basically that is what palindrome means, right? Is it right or not? Basically,
Right,
Yes.
if you stop here and if you divide into the middle, the next element must match this element, and the next element here must match with this element. Let's give an example. A, B, C, D. It must be D, C, B, A. Then only it is a palindrome. You now read from here. A, B, C, D, D, C, B, A. Now read from here. A, B, C, D, D, C, B, A. Got it? So the whole string, if you read from any side, it is the same. Eight elements here: A B C D D C B A. Even from left right side, A B C D D C B A. Correct?
Right. It's like a mirror image.
Exactly, it's a mirroring. If it is any, let's say we have a k here. Let's say between D and D we have a k, another element k. That's fine. There is no mirror. This is a middle element. If we have even number, which is in the first case eight elements, we have a mirroring. Every element has a mirror element. But if you have odd number of elements, there is one element which doesn't have a mirror, which is a k. Let's say k. You can ignore that because let's say a k doesn't have a mirror, but other elements have mirroring elements. Then it is a palindrome. Let's say in the place of c, if we have q, let's say this is not a c, this is a q. Then this q is not matching with c, then we can simply say this is not a palindrome, right? If you read from the right, it
Right.
becomes abqd. If you read from the left, it is abcd, but if you read from the right, it is abqd. So it is not a palindrome. If you read from the right, abqd dcba, so which is not equal to abcd dqba. So this is mirroring is a very helpful mechanism to figure out whether the given list is a palindrome or not. But how can we solve this? This is very problematic in terms of linked list. If it is arrays, I can simply divide in the
yeah,
middle and I can easily compare. I can have full access to the indexes. I can run
correct.
from anywhere to anywhere in the arrays. But in linked list, this is not possible. How can we do this? Is basically I can give you reveal the actual solution as well. But before, what data structure will help you? So what we do is what we are going to do is we'll navigate only half of the linked list. Only half of the linked list. Even that is also difficult. We don't know where the half is, right? You cannot say, oh, this is 10 elements divided by 2. That is, linked list has so many problems than arrays, but it has some advantages. And how we'll come to that part. Let's say you know the half. Let's put all the elements A, B, C, D. We got the first half. Now we need to check the mirroring. If we just need to check the mirroring. So when you get D, you need to check whether D is already there in the first half or not. When you get to the Q, we need to check whether that is there or not. Let's say it is not a Q. Let's revert back to the let's revert back to C here. Okay, this is C. So this is C. So now ABCD is there. When you go to the D, you will check whether D is there or not. When you go to the C, C is there or not in the mirroring. That way, by the time you reach end of this, if you able to find the mirror elements, then you definitely it is a palindrome. Mirroring elements means it's exactly at the same location. That is the problem. If you are using hash table, we can say, hey, D is there, B is there, A is there, but are they in the correct position or not? They have to match with this, right? That's why what we can do is once you complete the half, whenever you do the whenever you're starting the comparing D, you just need to compare the last element you added. Whenever you are at this C, you need to compare the last but one, the element which you added last but one. So let me ask this question.
Can we use stack?
Exactly, I'm about to say that. How can we extract the element which is just inserted? The best data structure that will give you the last element which is inserted is stack, right? So
Right, right.
that's what I want to answer from you guys. That's very good. So you answered it. So if you put in a stack, which is very beautiful data structure, which will help you to do that. So what I'm going to do is from the starting point, I will divide the entire linked list and divide in the sense I will only put first half of the elements into the stack. So I will put the A, and then I will put the B, I will put the C, I will put the D. Don't now I don't put any more. I will put only the first half. I will tell you how to figure out first half. I know linked list it's a problem, but there is a technique. There is a technique that you can definitely find out first half. I think I already discussed last week, but the same technique will help you here. So now we put only first half of elements into the array, not sorry, into the stack. So now what we are going to do is now let's start with D. Now if you take D, let's take the first top of the element from the stack and check is both are same. Yes, both are same. Now remove the element from the stack. Now let's go to the C. Now let's go to the C. Now compare with the top of the element. Top is here C. Now let's remove C. Now B, top of the element B, and now by the time you reach A, there are no more elements in the stack, and you successfully able to remove all the elements from the stack. That means this is a palindrome. In case of if you have Q here, right? What happens is A, B, C, D. D is matching with D, but when you are at the Q, this is a Q. This Q is not matching with C. Immediately you can say that there is no mirror element on the first half. So we can simply stop there, say this is not a palindrome. You no need to go through the end of the linked list as well. You just you can stop at the place where you did not find the mirror element. Is it clear?
Yes, Suresh.
Yeah,
Any-
Suresh, you mentioned Q also, right?
yeah.
Only stack will work, right? You mentioned Q also.
What is that?
No, you mentioned Q also.
No. If instead of C, if you have Q here.
Oh, I
See,
see, I see. That Q. Okay, got it.
so now
Elements.
I'm giving both inputs, one with the palindrome, one without palindrome. This is not a palindrome. A B C D D Q B A is not a palindrome, right?
Got it. Got it.
Make
Yeah.
sure our algorithm works for both the cases. So here you put A B C D, and D has a now you are starting with the second half. D has a mirror element which is good, but Q doesn't have the mirror element. Q must have a Q here, but we got the C here, right?
I see.
So this Q is did not match with C. So definitely that is not a palindrome.
Right. Right. Makes sense.
That's what I mean. So this when you are going from the second half, you need to compare with the top of the element. Basically, that's the reverse way of checking, right? D should match with D, C should match with C, B should match with B, A should match with A. Is it clear? This is the algorithm. Then what is the benefit here? The benefit here is, are we saving memory? Because if you compare
Yeah,
with the first algorithm, in the first algorithm we saved all the elements, but how many elements we saved here in the stack? What is the memory requirement?
half, like we are
Half.
storing half elements, like half of the
Exactly,
linked list.
exactly, exactly. So we are saving only, we are storing only half elements. If we have million elements, we are saving only 500k elements only. We need a half memory requirement compared to the first algorithm. So we optimized in terms of space, but did we optimize in terms of time? No, time you have to, like in the time complexity, you must traverse all the elements. Let's say in the in the place of A, if we have M or anything, we don't know until you traverse all the way to that element, right? So we must traverse all the elements. So there is no way of optimizing the time complexity, but space complexity wise, we optimized using stack. Got it?
Right. Like one question, Suresh. So,
Yeah.
when we are like when we are considering like time or space complexity, so we put constants outside. Like
Yes.
if our complexity is like big of n by 2, so we will take the constant part outside, like
No,
half.
no, I don't think so. Here, sorry, yeah, go ahead. Yeah, let you. I will let you continue your question. I will answer. Okay.
Okay, okay. So let's take example of like time complexity when we have two different linked lists, like one in a single direction and other in reverse.
Yeah.
So we were saying like to traverse, we will take big of n plus big of n. So it will be big of 2n,
Yes.
and we will take the constant part 2 outside, and then it will be big of n.
Yes.
So in the similar way, when like I'm thinking in a similar way when we are considering space complexity, so we can take one by two outside, like, and space complexity will be big of n, like.
I don't think so, because if I remember correctly, like a space complexity, basically if you are dividing, see, two of n. Why they are saying two of n is, why they are removing the two. Why they are removing two here is, if you say time complexity 2n is equal to, is almost equal to n. Why they are saying is, you are traversing n elements two times, isn't it? You traversed
Right,
all the elements first time and created the reverse linked list, and second time you are navigating again and elements and you are doing it. So basically, it's always depends on n. The time complexity depends on n. If n is increasing, your time complexity is also increasing. It's a order of n, means it's based on the n order. What is the n? I will do the same thing. This is also order of n, probably, you, if I'm talking to, but it is like space is like, it's a half number of elements. So maybe this is also order of n, because the space will change based on n. I agree with you. So because if space is like 10 elements, you are taking 5 elements of storage. If the given elements is 100 elements, you are taking 50 elements. So this is also order of n, because you are the space is also depends on the input. The input is given, right? If you are not saying, hey, whatever the input, I always take only 5 elements, you are not saying that. If you are saying like, even if you give 100 elements or 1000 elements, I will take only stack of 5 elements, then it is order of 1. Because order of 1 means one memory. I want one set of 5 kbs, or 5 into 2 10 kbs. You are saying like, this is order of 1. You are, if it is constantly taking some memory
right,
or some time irrespective of the input, then definitely it's order of 1. But here I agree with you, because the n is changing and your space complex is also changing. So it could also be the order of n, but in the, compared to the previous algorithm, this is better, isn't it?
right. Definitely,
It's not
definitely.
like
Like I
it's
was
a super
just
great algorithm. What I'm saying is, we did we I don't think we can optimize further. It is a little bit better optimization compared to the first algorithm. That's it.
definitely. Like we are taking half storage
Exactly.
now. Like it's definitely better. I was just talking in terms of like
Order. Yeah.
when we consider like right in order. Yeah.
Yep, yep. If you are saying order of something, definitely this is also for order of n space. I think order of n time. Sorry, Srini, are you following so far?
I need to understand a little more on the this
Yeah.
complexity part because I need to just recollect my basics.
Sure,
Yeah,
sure. I will. Yeah, we can touch base and
yeah.
we can discuss again. So yeah, basic. The I can give a small one more minute of explanation. So basically, order time complexity is always like based on the input. If the input is if the time complexity, okay, let's erase this. So if the time complexity and space complexity, right, and here is the input equal to n. So if n is changing, if your time complexity is also changing, let's say you are taking some k, but if n becomes m, if you are still having k, if you are solving the problem with this k minutes or k seconds, let's say it's time, right? So let's say your algorithm takes k milliseconds, ms, irrespective of the input n elements, m elements, or t elements, then you are always taking k milliseconds. That means your time complexity is order of 1. Order of 1 means your constant. Basically, you are saying whatever the input, I will have a magical problem that I can run in k milliseconds. Magic. You have a magic. You whatever the input, million elements, 100 elements, 1000 elements, don't care, I will be able to solve in order of 1. Then that's a magical problem which is called a constant time you are taking, which is order of 1. Got it? But if the time complexity is changing by the input, if n, you are taking, let's say, for the time 5n, that means 5 times, let's say we have 100 elements, 100 elements, 500 milliseconds, because 5 into 100, right? 500 milliseconds. If you have t equal to 1000 into 5, which is 5000 milliseconds, you are taking based on the t. Like if you are giving 100, I can solve in 500 milliseconds. If you are giving 1000 elements, I can solve the same problem using 5000 milliseconds. That means you are saying your time is changing based on the number of elements.
Hmm.
That means order of n. That means we are the our time is based on n. If order of n means based on the n, we are changing. I cannot say that, hey, I can give a problem, I can solve your problem in this constant time. It's not like that, right? Just an example, let's say you are
I
checking flights. You are checking a flights from one area to another area. Like if you are booking, like if you are putting like three stops, like it will take little more few milliseconds to figure out what is the route. If I am putting 10 stops, I want to go from here to here in the Google Maps. If you are putting more number of stops, that algorithm will take little more extra time to figure out the route, right? Depending on the input, the input is changing. If you are putting only one start and destinations, you will get the route within fraction of milliseconds. But if you are adding more number of stops, the algorithm will take little more extra time to figure out the route. Is it?
got it.
So that is called order of n. It's changing based on the n, changing based on the input.
I see.
So that's called order of n. Sometimes you will say, huh, I will be able to figure out n by 2. That means like half number of, like say if you are giving 500 elements, I can figure out within 250 milliseconds. If you are giving 1000, I can figure out less than like 500 milliseconds. So or sometimes we will say log n. Log n is another one. So log n is better than n, right? Logarithm, I think logarithm is a little more complex, but we should understand that as well. So we had very good discussion sometime back about the time complexity. So here is the one, order of k. Somewhere I wrote, yeah, log n. So this is n square, sometimes n square. So this is the best one, I think. Wait, yeah, somewhere I wrote the So first one is this. So the best algorithm, if you are solving with order of one, it's always best. If you could not solve with order of one, order of n is better. At least you are navigating all the elements only once and you are solving. If you could not solve in these two times stamps, like next one is the log n. Log n means which is greater than n, right? Is it correct? Correct or Modi? Did you understand? Is it smaller than n or I'm still need to confirm. So
Uh, I need I need to check. Like,
I think
just a
log n
minute
is
if I
better
have.
than n. Sorry, I think it comes like this. So if you understand, I will check, double check again. I could be wrong. First one is log and order of one, which is the ideal solution. You could not, if you could not solve with order of one, order of log n is better. Log n is less than order of n. If you cannot solve with a log n, you try to see if you can solve with order of n. If you cannot solve with order of n, it's order of n square. This is the worst. But there are some algorithms you can't solve, better than order of n square. N square means it's doubling. Let's say if I'm giving you 100 elements, you are taking 100 into square. Like if I'm giving 10 elements, you are taking 10 square times. So you are taking double the, you're taking time, which is double the input. Are you following?
Uh, yeah, yeah. Do you have order of n by 2? I
N by
don't
2
remember.
is n by 2 is fine. That's what n by 2 is fine, but which is almost is order of n. That's what we just debating. I think that space, but order of n by 2 is also good. I think, yeah.
For binary search, I believe most of the times it's
Yeah,
n by
yeah.
2, right?
But order of n by 2 is can be considered as order of n because it is changing based on the n, right? See, if it is 10 elements, you are taking 5 milliseconds. If it is 100 elements, you are taking 50 milliseconds. N by 2.
That
So it's
case,
changing based on the n.
true, true. But there is a little difference, right?
It's a
Suppose
difference. Yeah.
is order of n is same if you do a loop, but
Hmm.
if you do the same one with the binary search, you will solve the problem in n by 2.
Hmm.
So then we cannot say that both of them are order of n, right?
I need to check that. I still need. I'm not 100% sure because
Okay.
in a real times it is definitely better than order of n. I agree with you, but in terms of specifying order, maybe I'm not sure whether they will say it's also order of n. So usually if we have 2n, if we have 2n, we'll definitely remove that constant. We can simply say order of n, but we should not remove 2 here. N square is really bad, like you are
Yeah.
doubling. So
Yep.
here we should not remove. N square is different than 2n. So but anyway, these are the, I just want to give you a basic understanding of the this time complexities in space is also the same, right? Same thing, like I want if you give n elements, I'm taking 2n. 2n is like it's changing based on the n. If you are taking n square, same thing. So if you are taking only half n by 2 space is also similar. Or sometimes you will say, n plus m. So you have two arrays n and m. You need space of n plus m. That is the space complexity. Or time is also, we can think of that depending on number of space. Let's say I will use only one space. Let's say you are using only three variables in your algorithm. This order of three, irrespective of the input, you give 1,000 elements, million elements, 500 elements, I don't care. I just need three pointers or three variables, which is order of three, but three is considered as order of one because it's constant. You're always taking three variables irrespective of the input. So that's order of one, order of one space. It's similar to the time, like in the beginning I said, right? If you are solving irrespective of the input, if you are solving your algorithm in 5 milliseconds, that is a order of 5, or let's say 5 milliseconds, 5, or let's say 50 milliseconds, irrespective of the input, you are solving your algorithm in 50 milliseconds. That's order of one. Similarly, irrespective of the input, you are taking only three variables, which is order of one. For any
Got it.
constant time or space, that will be the order of one. Got it?
Got it. Got it. Yep.
Okay. Good, good, good. So we got
Thanks for clicking out.
the
Yeah.
things. I'm going to reveal the algorithm if you guys are clear on these approaches. Okay.
Yeah,
Now we still need to
just
solve one problem. In the second problem, right? So we have elements and how to identify the half, because we want to store only half elements into the stack, right? How to identify this half? That is something I will explain you here. There is a technique that we discussed last week as well. That's called a two-pointer approach. Do you know that, Modi?
Yeah, like I've used in arrays,
I don't
like
think
even to
so.
come.
Okay, okay, go ahead. Arrays
I was
doesn't
saying
require
like
two-pointer approach.
suppose if
Yeah, sorry. Go ahead.
okay, so if the similar if we have similar question in arrays, so
Hmm.
like we can take 2 pointers x and y, like put on like first position of array and last position of array,
Oh,
x on first and y on last, and then
hmm.
we can like keep comparing like first and last, second last elements. Like
Yep, yep.
in
That's
that
what.
way, I remember two
Yes,
pointer
yes,
approach.
yes.
Yeah,
That is a
that's
two-pointer
arrays.
approach in arrays. Yeah, that's a
Correct.
two-pointer approach
Correct.
in arrays. So here, two-pointer approach in linked list is little different. Here, the two-pointer approach in linked list, you can't do like, hey, here is one pointer, here is one pointer, because you cannot, you don't have access to the last
Right,
element. It's not a
right,
double linked list. You can't even traverse. It's a single linked list. You can't traverse in a reverse way, right? That's why we did not choose that algorithm. If it is double linked list, I totally agree with you. It's exactly like arrays. So you can start one here, one pointer here, one pointer here, and you can compare these mirroring elements until the both pointers becomes into the center. Then it's very easy to say whether it is a palindrome or not. If it is double linked list means like you can go back and forth. Every node has a back pointer and also front pointer. Srini, do you know the double linked list concept?
I totally forgot. Suresh, I have to recollect all.
No problem. So
Yeah.
basically, linked list has two things, right? The data and the next element, next pointer, right? Linked list points to the
Mm-hmm.
next element, and every element has two things: data and the next pointer.
Node and head, right?
No,
It's a
node,
basically
yeah,
node and head.
node, exactly, node. So in the case of double linked list, it has two things: data is in the middle, and two pointers. Like here is the next pointer, and here is the previous pointer points to this node, next pointer points to this node. So here is,
I
let's say,
see.
one more element here. This pointer points to this node, and this pointer points to this node. That's a double
I
linked
see.
list.
Got it. Got it. Basically, it has like instead of just node and head, it will has a like
Next,
the previous one. Yeah, head also.
exactly.
Okay, next head and previous head. I got it. Got it.
Next and previous. Every node has
Got it.
two pointers and one data. This data could be anything: integer element,
Right.
string
Got it.
element, number element, or employee object. Any object, you can put any object in the data, but there it has two other pointers. So we haven't discussed the double linked list. We will discuss maybe down the line. So
right.
there are few double. Yeah, here is the two
So
double linked list algorithms. But what Modit was
like
saying is,
one
if it is a double linked list, we should have used two pointers and compare simply. We don't need stack. If it is a double linked list, we don't need stack. Correct, right?
right. So and one example to remember double linked list like concept. So in music player, we have access to like we have access to playlists, so we can go and back
Hmm.
like we can change music.
Yep.
So
Yep.
maybe they use double linked list like to
Very good.
Yeah. Makes
Very
sense.
good.
That's a good one. Yep.
Very good.
yeah.
Very good example. Yeah. So now coming, the question I asked here is different. So how can you? So here we have here our second algorithm is we need to store first half. We need to store first half of elements into our stack. But how do you know what is the first half? How do you know one? The only way is either you need to count all the elements. Let's say you have 10 elements, then you will divide it by 10 divided by 2, which is 5. And then as you are going, you need to compare, you need to have a counter: 1, 2, 3, 4, 5. Then you put all the 5 elements into the stack. That's one option, right? So uh, but there is another option actually. So you can you can easily count half elements by using a fast pointer and slow pointer approach. Fast pointer FP and slow pointer SP. There is one technique that I explained last week as well. So that is what we use here. So I will quickly finish that. Okay, what is fast pointer slow pointer approach is, you both will start with the first element. Like fast pointer slow pointer will start with the same head element. Okay, now fast pointer jumps two elements at a time, whereas slow pointer just jumps only one element at a time. Okay, so what this helps is, by the time the fast pointer reaches the last element, the slow pointer will be at the middle. That is the technique here. So it's basically you're jumping two nodes, basically two uh, two nodes you are jumping. By the, so you will reach the end two times, like two times faster, right? By the time the slow pointer is only at the half, because the slow pointer is only jumping one node at a time. You guys got it? So I will show you the algorithm. So
Yes.
it is little tricky at this point, but if I show you the algorithm, probably you will be able to figure out. Okay, Trini, are you following?
Yes, yes, Suresh. Go ahead.
So I will show you the algorithm. Where is my mouse here? Come on. I think I went into the different monitor. I'm trying to see how can I bring back to this laptop. Come on. I don't know which. Oh, now I got it. Oh, this way. Okay. If I go this way. Okay. Anyway, I got it. So here is algorithm. First, let's go back to the same. Let's understand both the approaches, approach one and approach two. I have algorithm for both approaches. I will show you the algorithm finally. We will be finished in another 10 minutes. Okay. So here is the node. As we discussed, node has two things: data and next pointer. Here is the constructor, and here is the add links. Is basically it will add the links. So this is all main algorithm, main function, and these are all the different test cases. So we will discuss them later. So basically, yeah, I can show basically in the run test. I can show you one test case. So let's look at the positive test case. The positive test case is odd number of elements, or positive test case is even number of elements. Let's look at this one. So we created 1, 2, 2, 1, which is a palindrome, right? So I added 1 to 2, 2 to 3, 3 to 4. So the if I print the elements, it is 1, 2, 2, 1. So even if you read from the bottom, it is 1, 2, 2, 1, right? So E is palindrome. Okay. So what we are passing, we are simply passing the first element, and one is the head. We are passing the first element, and this algorithm will determine true or false, whether it is palindrome or not. Okay. So now let me show you the ease palindrome algorithm. This is the reverse and compare approach, which is approach one. So what we are doing is basically it will take 2n, and it will also take n space. It will take it is going to create another linker list, right? So what we do here is, uh, first step, reverse and clone. So what are we doing here is we are sending the head node, and it will give you the reversed linker list. Okay, I created a small method. What it does is it will clone the existing linker list without changing anything. It will reverse the linker list. Now there is another method I created called is equal. Basically I'm passing the head, and also passing the reverse linker list head. So this is step number 2. Step number 1 is reversing the entire linker list and create another one, and step number 2 is comparing the two linker lists. Okay, stop me if you are not able to follow. Okay, how this works, the reverse and clone is basically, here is the algorithm to do that. So we are taking another small, this is a node. We are taking another variable called head, and head, this node not equal to null. So new node equal to new node. Basically we are creating a new node every time. We are creating a new node with the data node dot data. Whatever the node dot data, we are creating a new node with the data. New node dot next equal to head, and head equal to new node. It is complex. This, in order to understand these lines, I would definitely recommend putting a white paper, pen and paper, and creating these boxes like this. Let's say you have 1, 2, 3, 1, 2, 3, right? So what we are doing is we are creating a new node. We are copying the data from here. Okay, now new node dot next equal to, what are we doing here? New node dot next equal to head. What is head here? Head is null. So new node head equal to new node, and node equal node dot next. So head equal to new node. Okay. Now head equal to new node. This is a new node. Okay. New node dot next equal to header. Oh, that's the way. Okay, got it, got it. Okay. What are we doing here is now one created, but one next one. What happens next is whenever the two is there, if we are creating another element called two. This new node dot head not next. Look at the line number 126. This next equal to this one. New node dot next equal to head. What is head? Head is actually pointed to this one, right? This new node dot next equal to head. Now new node equal to this one. This is the way to create the reverse linked list. This is another algorithm on its own. They will simply ask you, hey, how can you create a reverse linked list? This is the way. Okay. So next, no, next point node pointer to the next one. When you create three, we'll create a three, and three dot next equal to new node. No, not new node. This one, yeah. Three dot next equal to head. Head is pointed to two so far. Now head, now three node point three pointed to two. That way you created three, two, one. You are creating a node, and you are create you are pointing back to the this one. Finally the head pointed to the three. So that's how you create three, two, one. Okay, and you are returning the head. So go through this and put a pen and paper again. You will be able to understand. So next one is equal, which is very equal simple method actually. You have head one, head two, and you both will navigate is same or not, right? You have three to one, you have one to three, you have three to one. You compare each element, right? Which is simple. Whenever both elements are not matching, you simply return false. Otherwise, you proceed to the next element. One equal to head one dot next, head two equal to head two dot next. If both are finally reaching the null, that means they are equal, right? If one linked list is greater than or longer than the other one by any chance, of course it never happens. Let's say this one has three elements, this one has four elements, then one of this node will not be null, and so it returns the false. Are you guys following so far?
Um, this one probably like can you go from where you are calling this one? This is equal.
Here, so this is palindrome. Palindrome is the first function. This is the first step of creating reverse node. This is what the reverse node, and is equal is the second step. So finally this is,
Okay, basically like you are following the first approach, right? Here
yeah,
in
that's
this
what
in
I
this
said here.
example.
That's what I
Yeah.
said. We are
So
explaining the first.
you are basically yeah, reversing the linked list. Then you are comparing both of them. Okay,
Yes, yeah,
gotcha.
we haven't gone through the second approach. I will approach the second approach. I will explain now. So are we clear on the first approach? There are three simple methods I created. So this is the main method, main algorithm, and this calls the two sub algorithms, I would say. Modit, are you clear?
Yes, like I need to see like how to reverse a linked list. Like
Yeah,
I don't
it is tough,
remember,
Modit.
or like
Yeah, this is just
I need
four.
to like think and how to do it. Yeah.
Yeah, I just explained it. I can explain. Basically, what we do is reversing is like we have this linked list. We will access each node and we'll create a separate node and copy the data. Once you copy the data, we'll proceed to the next node. We'll create the second node, and the second node should point to this node. That is what we are doing. I would say these four lines are complex than ever. These understanding these four lines is super complex than any other thing. So very
Oh,
carefully understand. We need pen and paper. We need to have a clear mindset what is happening here. Okay.
so okay, line number 125. You are
Mm.
creating a new node and
Mm.
you are copying the data of the input
Yes.
into that new node.
Yes.
And the new node dot next, you are putting the head. So initially the head will be null,
Yes.
right?
Yeah.
So you are putting the head will be null,
Yeah.
and then
Now
the
we are
head
changing the
you are
head. And now I'm changing the head. Now head is the new node.
correct. Head is the new node, and then the next the node you are setting up as. node dot
Yes.
next.
Going to the next element because I am done with this element. I am done copying the first element. Now I am going to the second element in the input.
Wait. But the last line will be node dot next, right? Node
Yes.
dot next will be, in this particular case,
Mm-hmm.
the node that means the input. The
Input,
input
yeah, number
dot
two.
next.
Yeah. If you have three elements, we done with this element. Now we are going to the number two element. This is node.
So let's start with, so you pass the node one.
Mm-hmm.
Okay, you pass the node one here, and the head is null.
Yeah.
Okay, initially head is null,
Yes.
and you copied the node one data into a new node,
Yes. We
right?
are creating a new node. This is
And
new node.
right,
This
and
is node
new node, right?
one.
New node and new node dot. Could you go back
Yeah.
once?
New node dot next equal to head.
So new node dot next equal to head, which is null,
Null.
means that will be last, probably like a last
Yeah,
element. Okay, null.
exactly.
Mhm.
Yeah.
Right, and then new node dot, what you are setting. Okay, you are setting up the head to a new node.
Yeah. Now head becomes
Uh,
this is head. Head becomes this new node. Head is pointed to this new node. Until now, head pointed to null, right? Now
correct.
head
Head
pointed
pointed
this
to the new node,
new node.
new
Yes.
node, new node. Okay, go back. Yeah, new node, and node dot
Node equal
node
node dot
equal to
node dot next.
node equal to node dot next,
That means this node
means,
becomes
okay, the next one, next item means the two.
yep. Now it will
So
go
node
here.
equal to.
Yeah.
Hmm.
Again, we are creating one more new node and we are
So in that
copying.
particular case, node is not null,
Yes, node is not null. We are
not
creating
null.
one more node. We are creating one
One
more
more node,
brand new node,
right,
and we are
right,
copying the data. This is now the tricky part here. Now what happens is new node dot next equal to head.
correct. New node dot next equal to head. That is the one. That is the one.
So we are basically creating the reversing of this one. So one is connected to two, but here two is connected to one.
Correct.
Got
Two
it?
is
We are
connected to one.
reversing.
That's correct.
Exactly.
That's right.
So it one
So
did not
two is
connect to two
connected to
here.
one.
One is null. One is not connected to two here. One connected to null here.
Correct. Right. Makes sense. Yeah.
Now head is changing to 2. Next step
Mm,
equal to new node.
that's right. And the node is again the three. Got it.
Now node becomes 3. Now we are creating another node, copying the data. The same thing. New node dot next equal to 2. Now head becomes 3. Finally we are done with input, right? Now we are returning the head here. What is the head here? Head is 3.
Three. Right.
That means
That's right.
we essentially created a linked list head pointed to 3 to 1, which is reverse of the given list.
Right. Makes sense.
You understand? That's why I'm saying in order to understand this, pen and paper and write each steps. Modit, did you
It's
follow now?
yeah.
Modit, is it clear now?
Yeah, Suresh. Like I once I will do it by myself, like
Yep.
take one more example, it will be more clear.
Sure. Yeah,
Yeah.
this is very crucial. But anyway, now you understand the whole purpose of these steps, right? The algorithm is you understand the object to what we do on here, right? First one is reversing and
Yes.
then comparing. Okay. Now let's
Right.
jump into the
Right.
final part, which is stack. We are not using the we are not creating another linked list. We are only half n by 2 space complexity is n by 2. How we are doing basically is palindrome iterative method. This is iterative method. First one is reverse, but it is iterative method. As I said, we need to have fast pointer and slow pointer. Okay, and we also need a stack of integers. We are putting stack of because the input is integers. Push step one, push half of the elements into the stack. How do you find half is basically fast not equal to null and fast dot next not equal to null. So, so this is the condition. What we need to do is both fast and slow are pointed to head elements. We are pushing the elements into the stack. Slow elements because slow will navigate each element. So better to it's always better to use slow pointer to push the elements. Now slow equal to slow dot next, but look at the fast fast equal to fast dot next. We You guys need to understand what is this next dot next. Basically, we are jumping two nodes ahead. Okay,
Mm-hmm.
so by the time fast reaches the end, this is the condition. By the time fast pointer reaches the end, it will add all the elements. It will add half of the elements into the stack. Okay, I would recommend you guys put the pen and paper if you have some time this week, and run this algorithm, and you will be able to figure this out how this is working. You can take 5 elements, you can take 4 elements, you can take even number of elements, half number of elements. It will work for both. Okay, next, step number 2. This is a small step actually. If the fast becomes not equal to null, this is the condition. If the fast pointer not equal to null, it means there are odd number of elements in the list. If we have odd number of elements, we discussed in the middle, we discussed in the beginning, that element did not have any mirroring element, right? So we need to skip that middle element. This is the skipping part. We If the fast pointer is not null, if the fast pointer is null, that means even number of elements. We should not do this skipping part. Take pen and paper, run with an examples, you will be able to figure out. Okay, this is very crucial step to skip the middle element if we have odd number of elements. Next, step number 3. Now proceed with elements in the list and compare them with the elements in the stack. So now slow pointer is in the middle, right? We are proceeding with slow pointer. We don't need fast pointer anymore. Fast pointer is already reached the end of the linked list. We don't need anymore. We use the slow pointer only. What we are doing is, as we discussed, we are taking the first element from the stack and comparing with slow dot data. If the values did not match, then the list is not a palindrome. So return false. If not, slow equal to slow dot next. Simply it will navigate second half, and each time it compares with the top element from the stack. Finally, if you successfully able to complete the loop without returning false, that means it is a palindrome. Simply return true. Is it clear? Or I know it is complex to understand at the first in the first go, but I hope you are able to correlate with the discussions what we had.
Yeah, I think Suresh.
Awesome. Sandy, what about Modit?
Yes, Suresh, it's
Yeah.
clear.
I will send the link to this algorithm. We have clear step-by-step procedure. I would recommend take an hour in this week, and take an example like put take pen and paper, and also run with examples. Here is the different one. So initial list, this is 1 2 3 is not a palindrome. Initial list is 1 2 3 2 1, which is odd number of elements, right? Look at this. The 3 is actually the skipping. We should skip 3. It will skip the 3 in the algorithm, and it compares 2 with this 2 and 1 with this 1 in the stack. The true. And here is the even number of elements, 1 2 2 1. So there is no skipping will happen here. So 2 will be compared with 2, 1 will be compared with 1, and its palindrome equal to true. So you can take n number of elements, it will work. Awesome. Finally, we were able to discuss one big algorithm.
Nice.
I'm putting
Yeah,
in
it's
the
very nice, Suresh. Yeah,
Yeah, I'm putting in
it's
the
a good
comments.
suggestion.
Yeah, please go through the algorithm. You can save the link. I will send through Discord channel as well the link to this algorithm. Sorry, go ahead, Srini, you're saying something.
No, it's a good discussion, Suresh. It's yeah, it's little like recollected me probably like a long back, probably more than 15 years back. I think I went through a couple of them. So
Very good, very good. Yeah, this is what I do every week. It's a good discussion. Like
yeah,
it's really helpful for me as well to understand these algorithms, and and at the same time, it's a fun discussion. Getting different ideas, solving the problems, right?
Yes, it's very helpful. Yeah.
yeah, it's really good.
my point is always like apply these skills, apply these techniques in the different algorithm. I'm not I can't guarantee that you will get exact same algorithm. This is very good algorithm. This may come in the interviews like in Google, Amazon, or Facebook, wherever I'm, Microsoft. But the problem is we just need to apply these skills. These are different, like two pointer approaches and all. You can apply in different algorithms as well. So I'm running, battery is running low, so I think we'll stop it here, and we'll stop here, and we can continue next week. Okay.
Okay.
Awesome, awesome. Thank you, everyone. I'm going to stop recording here. Oh my god, it says battery is low. Let me stop recording.